Welcome back to our session. We're still looking at, our revision based on acids and bases. Right, now we'll take a turn to look at questions that are structured, your typical section B, questions, and see how best you approach those questions and how exactly you use some of the knowledge that you have learned in as far as acids and bases to apply that knowledge. Right. Now, the question says, sulfuric acid, the formula is given, H2SO4, okay? It reacts with water through a multi-step reaction. So we've got reaction 1 and reaction 2, right? Okay? Now, the first question says, is water acting as an acid or base in reaction 1 and 2? In reaction 1 and 2. So let's try and interrogate the role or the type of substance water is in the two reactions that are given. This is also based on the theories, right? Okay, but which theory is this exactly? This has to do with the Prosthetic-Lorry, right? So this is the Prosthetic-Lorry theory, okay? So Prosthetic-Lorry theory defines an acid as a proton donor, okay? While it identifies a base as a proton acceptor, okay? Simple and straightforward. So in an acid-base reaction based on the Prosthetic-Lorry theory, there is a transfer of protons. So there is a donor-recipient type of a relationship. So if we look at reaction 1, water actually accepts a proton, right? So the proton moves from the acid is transferred from sulfuric acid to water. Okay, so in this case, water acts as a proton acceptor, hence it is a base. Okay, similarly, the hydrogen sulfate ion, also donates a hydrogen ion. So in both cases, water acts as a proton acceptor. Right? So for that reason, we can simply say that water acts as a base in both reactions. Why? Because according to Prosthetic-Lorry, in both reactions, water is a proton acceptor. Right? Okay, so we've agreed that this is a base in the first reaction as well as in the second reaction. Why? Because in both cases, when water accepts, it gives us a hydronium ion. Okay, so similarly in the second reaction. So that's the kind of knowledge that we needed to be reminded of, right? Okay, then the follow-up question says, write down the formula of a substance that acts as an ampholyte in the given reactions. Okay, take note, it says reactions. This suggests that we're talking about both reaction 1 and reaction 2. And then after that, we're supposed to justify our choice, right? Okay, so if you look at this question, the key term or the key word in this question is ampholyte. Then we need to ask ourselves what an ampholyte is. In the context of acids and bases with respect to the transfer of protons, there is a proton donor, which is an acid, there's a proton acceptor, which is a base. So an ampholyte is typically that substance that can act as an acid or a base in different reactions, right? So now if we look at the first reaction, we say sulfuric acid is an acid, right? While water is a base. So this is an acid plus base. So when water accepts, what does it give us? It gives us a hydronium ion. So this hydronium ion becomes a conjugate acid, right? It means in this case, the hydrogen sulfate ion is a proton acceptor in the reverse reaction, hence it's a base, right? So the hydrogen sulfate is also still an acid because it donates, while water, we've identified that it is a base, right? So when water accepts, what happens? It forms a hydronium ion. So when this happens, it means the hydronium ion is an acid in the reverse reaction, or it's a conjugate acid, and then the sulfate ion is a base. Right. Now, if you look at the hydrogen sulfate ion, in reaction 1, it acts as a base, but in reaction 2, it acts as an acid. So simply it means that the substance HSO4 minus is an ampholyte. Okay, because in one of the reaction it acts as an acid, in the other reaction it acts as a base. Right. Okay. Now we move on to a different question that has to do with types of reactions. Right. It says write down a balanced equation of reaction between sodium hydrogen carbonate. The formula is given. Okay, and sulfuric acid. Also, the formula is given. So the key thing here, we need to understand that what type of a reaction is this in the first case? This is a metal carbonate plus an acid. So it's a type of a reaction. So what are our reactants? Our reactants is sulfuric acid, H2SO4, right? Plus sodium hydrogen carbonate, okay? To give us a salt. The salt that is going to be formed here is sodium sulfate. Okay, sodium sulfate, take note of the formula, SO4, okay, plus carbon dioxide plus water, okay? So this is like salt, this is a reaction that is used in the formation of salt. Salt plus carbon dioxide, okay, carbon dioxide plus water. Right. Okay. Now the balancing part comes in. If you look at the sodium on the right-hand side, it's 2 atoms. So we can also put it 2 moles there. Okay. That would kind of change also the number of carbon atoms. On the left now it's 2, and then on the right we still have 1, so we can put a 2 there. Okay. What about the hydrogen? How many hydrogens do we have on the left? It's 2 from the sulfuric acid and 2 from the sodium hydrogen carbonate. It means we can also put a 2 there. So if we can check if indeed our reaction is balanced, I think it would also give us the stoichiometric ratio in which these substances react with each other. So a mole of sulfuric acid reacts with 2 moles, right, of the sodium hydrogen carbonate to form 1 mole of the salt, 2 moles of carbon dioxide, and 2 moles of water. So we can also put an arrow there. So what does that arrow tell us? Because our focus is on the type of reactions, we want to appreciate that this is also, we can think of this as a gas forming type of a reaction, right? So this has a lot to do with the chemical formula and, you know, the whole stuff in terms of balancing, right? Okay, so we have, I managed to attempt that. Now let's look at the other question, which says, consider the following balanced equation. Now this equation has been balanced for us already. Now we are saying we don't need to temper around, you know, the stoichiometry in terms of, you know, the stoichiometric ratio in which they react. So we can simply interpret because it has been balanced for us. Okay, but the main focus in this question, it says, identify the type of reactions and give a reason in to support your answer, right? Okay, so let's look at the first one. The first reaction, it forms a salt. Let's take it from that end. It forms a salt, water, okay, plus carbon dioxide. Okay, so we were trying to work backwards. If a salt is one of the product formed, it means that an acid should have been you know, one of the reactants. So would identify sulfuric acid as an acid, right? Okay, but for us to get carbon dioxide, here we also want to recognize that this is a metal carbonate. Zinc is a metal carbonate. Okay. Now, we also want to say, okay, this is a type, what type of reaction forms salt? We know these are acid-base reaction, okay? So this is an acid-base type of a reaction. How did we arrive at that? We looked at the type of products and worked backwards in terms of the reactants so that we can be able to classify this reaction. But also, even if you keep track of the oxidation numbers, zinc is +2 on the left, and plus 2 on the right, okay? Also, you look at the sulfate is still the same, okay, also in that case. So as a result, this can be a redox reaction. It's an acid-base reaction in terms of proton transfer. But the easiest way to classify this is to look at the products and work backwards to try and identify the types of reactants so that we are able to arrive at the type of reaction. So this is typically an acid-base type of a reaction. Right. Now, we've got another type of a reaction, and we want to also try to think about the reason why we would classify this reaction as a specific type. Right. So this is a reaction between a metal, okay, and an acid. Right. This is a reaction between a metal and an acid. We are getting a salt, okay, plus hydrogen gas, okay. But what is important here is that we need to also keep track of the changes in the oxidation numbers of these substances, right? So what are we saying here? We are looking at zinc. Its oxidation number is 0. Now we're going to apply the rules of assigning oxidation numbers. So there's a whole lot of knowledge that we have gained that we need to bring to the fore and try to apply so that we make sense of this scenario, right? So if we look at zinc, for argument's sake, this side zinc is plus 2. Right? It's plus 2. And then also, if you check, the zinc undergoes, loss of electrons in this case. While if you check the sulfate ion, in this case, the sulfate ion is a spectator because its oxidation number does not change. So we can represent the change in the oxidation number of zinc using a half reaction. So this is going to be zinc to give us what? Zinc. Okay, just to correct that, this is going to give us zinc 2 plus, okay, plus 2 electrons, okay. Now, immediately we are thinking this has to do with loss of electrons. So this is oxidation, okay. This is an oxidation half reaction. We're onto something now. But if we look at hydrogen, in this case, the hydrogen is 2 plus, okay. So it's 2H plus, okay. These two of them, okay, plus 2 electrons, okay, because the oxidation number of hydrogen in its molecular form is 0. It means these hydrogen ions, they gained electrons. What does that give us? It gives us H2, okay? Now, there is a transfer of electron from zinc to hydrogen ions, right? So this is a reduction half reaction, right? Okay, so definitely, once we have got oxidation and reduction, this gives us a redox reaction, okay? Why are we saying this is a redox reaction? Because this involves a transfer, okay, of electrons, okay? This involves transfer of electrons. Hence, we have managed to arrive at the oxidation and the reduction half reaction. So over and above, the transfer, we managed to keep track of the changes in the oxidation numbers. So this is definitely a redox reaction, and the reason for that is that there is a transfer, which is loss and gain of electrons. Right.
Is he writing up?